Okay, welcome to part 3 of chapter 20. So we're just going to do interference and beats and the AM and FM radio idea. So interference we talked about before, how there can be constructive interference when waves are in phase, destructive interference when they're out of phase. And how waves are overlapping, and that's what produces the interference. Lots of pictures here, just fun to look at. Okay, all right. So anyway, when you have two transverse waves, those are what we talked about before, but it works equally well with sound waves. So when you have a wave with a compressed area on top of another location, of same location, another compressed area, then that adds up to a more compressed area. So you get higher pressure. And so that's increased amplitude or increased intensity, which is the way we talk about sound intensity. That's the amplitude, the loudness. And the same thing if you have out of phase waves. You can have a sound wave that has a compressed area, but it overlaps a rarefied area. So these are out of phase. And so the molecules just return to their natural scattered state. There's no pattern left. And so you get silence. That would be destructive interference. Now, this can actually happen in speakers. It usually doesn't, but it can because they usually make sure that the speakers aren't playing exactly the same thing. And but it is possible if you set up your speakers to play exactly the same simple signal, then they can actually you can reverse one of the speakers so it's going out of phase with the other, and you can actually get a diminishment of the sound. Now, so here we've got two speakers. Here the waves are coming in phase. Here they're out of phase. And that would be by half a wavelength. That's what gives you that out of phase appearance where the trough meets the peak. And the thing is that you can actually have the sound cancel out. Now, usually this isn't a problem, like I said, because they try to make speakers that don't play exactly the same thing. The other reason is we have two ears. So if it's out of phase at one side of our head, the other side it's not out of phase. So we still would hear it. It wouldn't be as loud, but we still would probably hear it. So usually if we do this in a classroom, we have to cover one ear so that we just get the effect in the other ear. Now this can be useful if you want to cancel noise. So noise canceling headphones actually have a microphone that is quickly detecting the sound that's coming in, and then it produces a mirror image wave pattern, so an out of phase version that goes into the earphone. And that cancels out the outside noise. So this is really important for someone with a jackhammer to protect their hearing. Or in this case, a person in an airplane. Airplanes are very noisy, but you still want to hear what the traffic controller is saying. So the sound that's coming in has to get canceled from outside. So they have noise canceling headphones. My husband uses them because our offices are now here in this house, and he can hear me talking to students, and there's no door between us. So he likes his noise canceling headphones too. So anyway, so sometimes you have to cancel sound out. So there's some sound coming in, the noise, an anti-noise signal is sent, and you end up with no or very little outside noise coming through. Now, those are more expensive than just regular headphones that block sound because they do have the microwave aspect. Okay, now another thing that can happen because of interference is a phenomenon called beats. And beats happen when you have waves that are not quite in phase and not quite totally out of phase because they are actually different frequencies. So because they're different frequencies, their wavelengths are different sizes. So they might match up in some places and produce constructive interference. But then, because their wavelengths are out of sync, then at other places you will have a rarefaction area lined up with a compression area, and you will get destructive interference. And this actually forms a pattern of destructive, constructive, destructive, constructive. And so you actually hear the sound going louder and softer and louder and softer, and it produces a whole new frequency of sound, which is called the beat frequency. And the beat frequency is the difference between the two original frequencies. So if one of these tuning forks is 256, middle C, and the other one is 258, then the beat frequency, I can take 258 minus 256, and you will hear a sound of 2 hertz. And that's the beat frequency. So you will hear a sound that's going, ooh. That's how it sounds. Ooh. Okay. But that would be twice per second. If they were further apart, you might hear woo, 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 or you might hear woo, 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 woo. That's the beat frequency. Okay, so let's go listen to the beats. This can happen optically too. It's sort of an explanation. Here we've got some combs lined up. One of the combs has 12 teeth per inch. The other comb has 8 teeth per inch. And so you can see how when they're overlapping each other, some places they line up and block light. Other places they line up and allow light through. So you get a whole new pattern, which is 4, 1, 2, 3, 4 per inch. Okay, so you get about 4 of these in an inch. So 12 minus 8 is 4. And so this is what happens when you try to take a picture of your computer screen and you get those weird swirly effects. That's a moire pattern, which I'm not sure if I'm spelling it here correctly. Anyway, so that's what happens then, because the computer has a grid and your phone has a grid, and if they're not lined up, then you get the moire pattern. Okay, so let's go look at some beats. So here I have 2 tuning forks. One of the tuning forks has weights on it, so I can adjust it. And the other tuning fork is 256. So when I play them together, you will be able to hear the beats. So there's 256. Here's the other one. A little bit deeper sounding. Okay, if I play them at the same time, hear that woo, 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 woo sound. About 2.5 per second. Okay, now I can also do that with my iPad, because I have some, oh, wait, what happened? It was right there. This app that I've got on, it's just called Sound Generator. And I can play different frequencies of sound. So I've got, let's set one to 300. Let's turn up the sound. Okay, so hopefully you can hear that. So one is about 300, and oh, I haven't got to 300 yet. Gonna crank the other one up. Okay, so one's at 302, one's at 306. So now you're hearing the beat frequencies of 4 per second. And if I change this one down to 300, now you hear 6 per second. Right? The further apart they are, then the more beats per second you hear, until they're so fast that you can't really count them well anymore. Okay, so now they are like 100 apart. So that sound would be a cycle of 100 hertz. When they get close to each other, that's 307 and 306, so that's 1 hertz. Now they're both at 306, so that's all you hear is 306 because there's no beat frequency. They're at the same frequency. Now I can also add a third player. And I can get a complicated pattern because I now have beat frequencies from all three sound sources combining with each other, and then their beat frequencies can combine with each other. So I get a 2 hertz from the 304 and the 306. I get a 4 hertz over here, but I also get a 6 hertz from the 304 and the 310. Anyway, it's lots of fun to play with beats. So that program is called Sound Generator, if you ever want to. I think I actually had to pay some money for that one, but not much. Okay, stop. All right. Okay, so that is the idea of beats. Somewhere around there. Okay. All right. And so there's just some problems here. 3 tuning forks have frequencies of 324, 326, and 330. What beat frequencies result? So again, each pair, so I would have 330 minus 326 would give me a beat frequency of 4 hertz. 326 minus 324, right? So these two together would give me a beat frequency of 2 hertz. But I also would get from 330 to 324 that would give me a beat frequency of 6 hertz. And then it's possible that those would affect each other, but 4 minus 2 would just give me 2 again. 6 minus 2 would just give me 4 again. And 4 to 6 would just give me 2 again. So anyway, so I wouldn't get anything new. I wouldn't get any new frequencies here. Okay, so, but it is possible to be getting new frequencies from the beats, from the beat frequencies. Here's a tuning fork playing to tune a piano. The piano string and the tuning fork are played at the same time. So if you've ever seen in a movie or something, somebody comes to tune a piano and they whack their tuning fork and then they're changing the string, ding, 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 they're playing the piano to hear it and they're trying to tune it. Well, that's what's going on. They're trying to listen for the beats. That's how we used to tune musical instruments. So I used to tune a guitar using a tuning fork, and actually I used to tune a harp with a tuning fork. So anyway, so you usually tune 1 or 2 strings, and then you have to, just use your ear because you don't want all those tuning forks. So you just use your ear to guide you on the rest of it. Anyway, so, but yeah, beat frequencies are useful in that way. Nowadays, of course, I use an electric tuner on my phone called Guitar Tuna. which is fun. Okay, so an app. So anyway, so there's a beat frequency of 4 hertz that's heard. What are the possible frequencies of the string? Well, the tuning fork is 440, right? So in other words, you can turn this equation around. You're looking for one of the frequencies. And so that's going to be your beat frequency plus the other frequency. But the thing is, you don't know which one is which, possibly. So really, you have to say plus or minus the beat frequency. So the 440 could be plus 4. So it could be 444. Or it could be 440 minus 4. Okay, because you don't know which one is the F1 and which is F2, which one's higher, which one's lower. To be sure, then he could tune it, crank it so it's a little bit higher. The piano string, he could make it a little more tight. So how can he be sure? Make the string a little more tight. If he hears more beats, then he knows he's going the wrong direction, right? Because that would mean they were further apart. So if he hears a higher beat frequency, like 5 or 6, so you want to tune, so you want to crank the handle the other way, and till he found that it was actually tuned to 440, and that's when the beats disappear. So that's when you're tuning. You have to tune till the beats go away. Okay. All right, so the last part of this chapter is about AM and FM radios. And AM means amplitude modulated. And FM means frequency modulation. And usually AM radio stations are in kilohertz, and FM radio stations are in megahertz. Okay, so we'll talk about why that is, along with describing what those are. So this first one is your AM, and your second one here is your FM. Okay, so what's going on? Well, this is the signal that you want to play. Okay, so that's your music. And this is so that's the signal that you want to play, your music, okay. And then this one here is called your carrier signal. That's what the FCC, that's the frequency that your radio station is allowed to transmit on. And you usually get a range of frequencies as possible. But AM have to stick real close to their frequency. FM is allowed a range because they are frequency modulated. Okay, so what happens is, so this is your carrier signal. And so for the AM station, being amplitude modulated, it takes the original pattern that you want and it places that on top of the carrier signal, and you end up with this. Okay, so this is what's sent out by the radio station. So that's your amplitude modulated signal. And the thing is, that goes out into the world, and then there is noise. And that noise adds into your signal. So now it looks like this. And when it gets to your radio, the radio cuts part of it off. And then it tries to detect what the original one was. But you can see here now, the noise is in there. They weren't able to get rid of the noise. So that's why AM radio stations usually do talk radio, they do rock and stuff, yeah, but they don't usually play classical music on AM stations because of the noise would ruin the delicate music of the classical music. So if you want really good sounds, then you need to be on FM. So on FM, what happens is that the carrier frequency can be modulated. And so you have a different range of frequencies, and that's possible up in the megahertz range. Then you can change it by kilohertz and still be close to your number that you're assigned. So anyway, so the signal that you put in is interpreted as a frequency change. So you can see for the peak here, that's the peak, you've got higher frequency. For the trough, you have lower frequencies, and so on. So you've got a signal, but it's all done by frequency. Then when the noise comes in, it still makes it look a bit weird, but the noise doesn't affect the frequency. And so when it gets processed by the receiver, they don't need the height, the amplitude, which is what the noise changed. Didn't change the frequency. So they can just reinterpret the frequency. You can see they still got the peak and the trough. And so you get back a beautiful, exact mirror image of the original signal. Okay, so anyway, so we get a lovely signal back, not mirror image, meaning reverse, just like looking in a mirror. It's perfect. Okay, so anyway, so yeah, so that's why FM radio stations are more exact, and so they're used for when you want music to be closer to the original. So why do we use AM at all? Well, AM has some other advantages. One of the big advantages is when you're out far, far away from a city, about the only radio signal you can hear is AM, because the and of course our country is very large, so we can be far away from a city pretty frequently. What happens is that the AM signals can bounce off the ionosphere. So the city can be here, it'll bounce off the ionosphere, and your truck or car can pick it up over here. Whereas the FM radio station would have faded out by that time or been blocked by the curvature of the earth. So yes, so when people are far out driving down in Wyoming or Texas or far away from a city, then it's AM that you want. That's what you got to listen to out on the road. Okay, so that is, I think, oh, that's just the pictures. The end of the chapter. Okay, see you in chapter 21.